Okay, YouTube, in this video what we're going to do is consider the inverse of a rational function and how we might determine whether or not it itself is a function. And so what I want to start with is essentially this function right here. We have f of x equals 2 over x plus 3. And what I want everybody to see is kind of the graph over here on the right-hand side. We can see that this graph here easily is in this, I suppose, a over x minus h plus k form. But it's easy to see that really this is just our rational function 2 over x that's been shifted left 3. So we would have this vertical asymptote that runs right here. And of course, because we didn't shift it up or down, we would have this horizontal asymptote that runs here. So I'm going to label these out. We have y equals 0 and x equals negative 3 here. But this would be the graph of our rational function. Now what we want to do first, according to the instructions, is determine whether its inverse f would also be a function, and then find that inverse. And so to determine whether or not f would be a function, let's recall what we mean is the definition of a function. We say all functions are one-to-one. And that is to say that all or every, let's do that, every x value must only go to one y value. So as we represent this in roster notation, you could look at this as all of these x values on the left here, they go to a y value on the right, but they're only allowed to go to one y value. And so as we look at that as being a function here, what we've seen in the past is that if every x value goes to one and only one y value, then our graph passes what we call the vertical line test. And that is to say that, say, each of these individual x values here only went to one y value on our graph, and therefore the vertical line test just says if you can draw a vertical line anywhere and it hits your graph just one time, then it is a function. Now the interesting thing is, what do we know about inverse functions? Well, we know that their domains and ranges switch, and we also know that they are reflected about this line y equals x. So this is our line of reflection here for inverse functions. And by knowing this, we'd say that domain and range really are the things that switch. But if you had a function, okay, that reflects over that line y equals x, then all of a sudden you would have a function that kind of looks like a mirror image of itself. So that is to say that if we were to have, say, something like a parabola, okay, its inverse, as we reflected over this line here, would look something like this. And the thing that I really want to note here is that something like a parabola, once you find its inverse is not a function, and we could tell because it fails the vertical line test. So to be very, very clear on this, how could we have told you that the inverse of this parabola would not itself be a function? Well, then before inverting it, we could have done what we call the horizontal line test. So in order to determine whether or not the inverse of f is a function, okay, we're going to write a little note here. We are going to use the horizontal line test in order to determine this. So use the horizontal line test on the graph of f of x in order to determine if f inverse will be a function. That's going to be our method for determining whether or not the inverse of f is itself going to be a function. So when we look at this graph of 2 over x plus 3 here, what I notice is if I were to draw a horizontal line anywhere, let's switch the color over to green here. If I draw a horizontal line anywhere on this graph right here, then it only ever hits my graph in one spot, which means when I do find the inverse, it's going to flip over such that it actually passes the vertical line test. And so what we'll write here is determining whether f is the inverse of f is a function. We would say that the inverse of f is a function, and I'll type this here a little bit faster. The inverse of f of x is a function because its graph passes the horizontal line test. So the first thing we've assessed is that the inverse actually exists, and the way to get that is we actually have to go graph it and see if it passes the horizontal line test. Now when it comes to actually finding the inverse, here's the neat thing about finding the inverse. We've found plenty of inverses in the past, and that is to say that, let's undo that there. We have seen that when you find an inverse, what we're really doing is switching the domain and range of a function, or in other words, switching all of the x's and the y's. So the way this is going to work here, and I'm sort of running out of room, is that we have our initial function. I'm going to write it as, instead of f of x equals, I'm going to write it as y equals 2 over x plus 3. And the very first thing we're going to do here is switch colors. Why? Well, because this right here, the moment I switch my x's with my y's, this is the inverse function. So the inverse, I want to know if it is a function. We did determine that it is a function. What we want to do is solve for y. So what makes this a little bit interesting is when you have an equation like this, how you get y out of the basement is to take both sides times literally times the factor here, y plus 3. And so because I can't draw on this right here, let's see if it'll let me bring to the front. If we were to take the left side here times a y plus a 3, then we would still have equality, and what we end up with is this situation where on the left we have y plus 3 times x equals 2. So again, remember, we're trying to solve for y in terms of x. The easiest way to do this here is not to distribute the x, but to divide the x here on both sides. And what we get is y plus 3 equals 2 over x. And so subtracting 3 here, minus 3, we would get y equals 2 over x minus 3. And we're going to rename this here. This is our inverse function of x. So 2 over x minus 3. So I want to explore this graphically here. And the way we're going to do this is just go ahead and pop over online to a Desmos graph. And so our initial function, let's go ahead and graph this, f of x, was equal to 2 over the factor x plus 3 here. And so we can see this initial graph here. Put this in projector mode. I'll flip this over to a black graph here. You can see that at x equals negative 3, we have a vertical asymptote. And at y equals 0, we have a horizontal asymptote. What I'd like to do is let's maybe make both of these red, and we'll make them dashed. And so we could see our asymptotes very clearly here. If I get that done. Boom. Okay. So with something like this, we said that its inverse function, I'm going to call the inverse function g of x. But what we found out was g of x was actually equal to just 2 over just x, and we shifted down 3. So our inverse function here, perhaps we should put this in a different color here. Let's make this one blue. And so what I want you to see with the blue graph here is that if I were to switch my domain and range, then the asymptotes would switch also. And so instead of x equals 3 and y equals 0, I would really have x equals 0 and y equals negative 3. And if I were to switch these over, maybe perhaps to, let's do these in green and make them dashed here, you could see that the domain and range just switch here on both of our graphs. And last but not least, I'll even put in this line y equals x. And we'll do this. Well, how about we throw that in an important color here? How about purple's important? Well, here's the deal. We can see that these graphs are mirror images of one another and that their asymptotes just switch and their domains and ranges switch. So with respect to finding the inverse here, we did find out that the inverse was a function by graphing the original function and saying it passes the horizontal line test. But here we'll just say f inverse of x is equal to 2 over x minus 3. So that's how you find an inverse function if it is rational. Cheers.